Imagine a force. It is completely invisible. It travels at the speed of light. It makes no sound. Yet this silent wave possesses the power to send our modern civilization back to the Stone Age. This is the nature of an electromagnetic pulse, or EMP. It's not a bomb in the traditional sense. It doesn't flatten buildings or create a mushroom cloud on the ground. Instead, its target is the very lifeblood of our interconnected world: electricity and electronics. An EMP is a sudden, intense burst of electromagnetic energy. Think of it as a flash of lightning, but on a colossal scale, capable of blanketing entire continents in an instant. Understanding this phenomenon is crucial, for our reliance on technology makes us uniquely vulnerable to its unseen power. To grasp the concept of an EMP, we must first journey into the realm of the electromagnetic spectrum. This spectrum is a vast cosmic keyboard, and visible light is but a single key. There are other keys, other forms of light we cannot see, like radio waves that carry our favorite songs, microwaves that heat our food, and X-rays that let us peer inside our own bodies. All these are waves of energy, composed of oscillating electric and magnetic fields dancing through space. They are the fundamental messengers of the universe, carrying energy and information across immense distances. An EMP is simply an extraordinarily powerful broadband burst across a wide range of these frequencies, from very low to very high. It's a sudden, chaotic shout in a world built on carefully controlled electromagnetic whispers. Our modern world is a symphony of these whispers. Every mobile phone call, every satellite transmission, every transaction zipping across the internet is a finely tuned vibration in the electromagnetic field. The power grid that lights our cities and powers our homes is a colossal circuit, guided by delicate electronic controls. These systems are designed to operate within specific, gentle parameters. They are not built to withstand a sudden, overwhelming surge of electromagnetic energy. An EMP acts like a cosmic hammer blow to this delicate, glass-like infrastructure. It doesn't just disrupt communication, it has the potential to induce crippling electrical currents, frying the very circuits that underpin almost every aspect of our daily lives, from transport to banking to healthcare. The importance of understanding EMPs, therefore, cannot be overstated. We live in an age defined by our mastery of electrons. We have woven a global web of technology that has brought us unprecedented prosperity and connection. But this intricate web is also our Achilles heel. An event that could disable this web, whether natural or man-made, represents a profound threat to global stability. It's a threat that doesn't announce itself with a roar, but with a silent, instantaneous flash. By exploring the science behind this invisible force, we can begin to comprehend our vulnerability and, perhaps, learn how to shield our world from the ensuing darkness. The cosmos is full of powerful forces, and this is one we have brought upon ourselves. So where does such an immense burst of energy come from? An EMP can be born from the most powerful events known to humanity and in the cosmos. The most widely discussed source is a nuclear explosion. When a nuclear weapon is detonated high in the atmosphere, a sequence of events unfolds with incredible speed. The explosion releases a torrent of gamma rays, which are extremely high-energy photons. These gamma rays travel downwards and collide with atoms in the upper atmosphere, primarily oxygen and nitrogen. This collision is so violent that it knocks electrons free from their atoms, a process called the Compton effect. These newly freed, fast-moving electrons are then grabbed and spun by the Earth's own magnetic field. This interaction with the Earth's magnetic field is the key. As the high-energy electrons are forced to spiral around the planet's magnetic field lines, they generate a powerful, rapidly changing electromagnetic field. This is the EMP. It's a grand-scale version of how a generator works, where moving a magnet near a wire creates a current. Here, a massive shower of electrons moving through a magnetic field creates a gigantic pulse of radio waves. A high-altitude nuclear EMP, or HEMP, is comprised of three distinct parts. The first, called E1, is an incredibly fast and intense pulse that fries microelectronics. The second, E2, is slower and similar to lightning. The third, E3, is a very slow pulse that can induce damaging currents in long electrical conductors, like power lines and pipelines. However, nuclear weapons are not the only source. Nature itself can produce EMP-like effects. A powerful solar flare can trigger a coronal mass ejection, or CME, hurling billions of tons of charged particles towards Earth. When this solar storm interacts with our planet's magnetosphere, it can induce powerful geomagnetically induced currents, or GICs, in our power grids. The Carrington event of 1859 is the most famous example. It was a solar storm so powerful that it caused telegraph systems across Europe and North America to fail, with some operators reporting sparks leaping from their equipment. While technically different from the fast pulse of a hemp, the end result, widespread electrical grid damage, is alarmingly similar. Man has also engineered smaller, non-nuclear EMP weapons, sometimes called E-bombs. These devices use conventional explosives to generate a directed high-power burst of microwave radiation. One common design involves a flux compression generator. In this device, a chemical explosion rapidly squeezes a powerful magnetic field, converting the explosive energy into an intense electromagnetic pulse. While their range is far more limited than a nuclear EMP, they could be used to target specific high-value facilities like a military command center, a financial district, or an air traffic control tower. They represent a more tactical, but still highly disruptive, form of electronic warfare, a silent weapon for a digital age. How does this invisible wave of energy actually destroy our precious electronics? The mechanism is surprisingly simple and elegant. Every piece of metal, from a long power line to the microscopic copper traces on a circuit board, acts as an antenna. When the powerful sweeping electromagnetic fields of an EMP wash over these metallic objects, they induce electrical currents and voltages within them. This is the principle of electromagnetic induction, discovered by Michael Faraday. The problem is that the currents and voltages induced by an EMP are millions of times stronger and thousands of times faster than what these devices are designed to handle. It is the electronic equivalent of a gentle stream suddenly turning into a tidal wave. Consider the delicate world inside a modern microchip. The transistors, the tiny on-off switches that form the basis of all computing, are incredibly small, sometimes only a few atoms wide. They are designed to operate on just a few volts of electricity. The E1 pulse of a nuclear EMP can induce thousands of volts in a fraction of a second. This overwhelming surge of voltage blasts through the fragile silicon gates of the transistors, melting them and permanently destroying the chip. It doesn't just turn the device off, it physically burns out its brain. Anything containing a microprocessor, cars, phones, computers, hospital equipment, water pumps, becomes a useless piece of metal and plastic. On a larger scale, the effect is just as devastating. Long conductors like power lines, railway lines, and communication cables are exceptionally good at picking up the energy from an EMP, particularly the slower E3 pulse. They act as giant antennas, collecting the pulse's energy and channeling it into the electrical grid. This can overload and destroy the massive transformers at electrical substations. These transformers are the backbone of the grid, and they are notoriously difficult and time-consuming to replace. A widespread loss of these transformers could lead to a nationwide blackout lasting not for days or weeks, but for months or even years, plunging society into darkness. The scientific numbers are staggering. The E1 component of a hemp can reach a peak electric field strength of 50,000 volts per meter. For context, the field strength for a typical radio station is measured in microvolts per meter. This immense field strength is what makes an EMP so indiscriminate. It doesn't need a physical connection. It couples its energy directly into circuits through the air. In 1962, a high-altitude U.S. nuclear test called Starfish Prime, conducted over the Pacific Ocean, provided a chilling real-world case study. The resulting EMP was far stronger than scientists predicted, causing damage to streetlights, telephone systems, and burglar alarms in Hawaii, nearly 1,400 kilometers away. It was an accidental glimpse into the electronic chaos an EMP could unleash. Faced with such a potent and invisible threat, is our technological society defenseless? Not entirely. The principle of protecting against an EMP is conceptually simple, though often difficult and expensive to implement in practice. The most effective defense is known as a Faraday cage. Named after the same Michael Faraday who discovered induction, a Faraday cage is a container made of a conducting material, or a mesh of such material. When an external electromagnetic field hits the cage, it causes the electric charges within the conducting material to redistribute, canceling out the field's effect inside the cage. Anything within this conductive shield is protected from the EMP's energy. This principle can be applied on both small and large scales. Critical military command centers and essential infrastructure are often housed in buildings specifically constructed to act as large-scale Faraday cages. These structures have metallic skins, specially designed doors and windows, and filtered power and data lines to ensure no part of the pulse can leak inside. On a smaller scale, sensitive electronic components can be stored in metallic boxes or even simple, tightly sealed bags made of metallized plastic. However, retrofitting an entire nation's infrastructure to be EMP-proof is a monumental and costly undertaking. Every wire that enters or leaves the shielded enclosure must be filtered to block voltage surges, adding to the complexity. Beyond simple shielding, another layer of protection involves hardening electronics. This means designing circuits from the ground up to be more resilient to voltage surges. This can involve using components with higher voltage tolerances, adding surge protectors like transient voltage suppression diodes, and incorporating clever circuit layouts that minimize the antenna-like properties of the wiring. For the power grid, this could mean installing devices that can rapidly disconnect transformers from the long lines during an EMP event, or having a stockpile of spare transformers ready for deployment. The challenge, as always, is balancing the cost of this protection against the perceived risk. Experts remain deeply concerned about our vulnerability. The U.S. EMP Commission, in its reports to Congress, has repeatedly warned that our civilian infrastructure is almost completely unprotected. Our society is a system of interconnected systems. A failure in the power grid cascades into failures in communications, transport, finance, food distribution, and water purification. While military systems are often hardened, the civilian world upon which the military and society depend is left exposed. The ultimate conclusion is a stark one. The science of the EMP is well understood, as are the methods of protection. The question is not one of physics but of will and priority. In our race to build a brighter, more connected world, we must not forget to build the shields necessary to protect that light from being extinguished in a single, silent flash.